It's okay, guys. Let's talk about how a polynucleotide strand or chain is going to be formed. And simply, poly means many, nucleotide means so many nucleotides. And simply, these nucleotides are formed by condensation reaction, okay, between a sugar, the OH group on the sugar molecule, and the OH group on the phosphate group. Okay, you saw that in one nucleotide, if we have this, okay, this is your nucleotide, you have this pentose sugar, then you have the organic base, and then you have a phosphate group. Now this is carbon, and the carbon bonded to this phosphate group using the OH of the carbon and the OH of the phosphate group, where they do condense to release a water molecule. So the same thing happens, on this carbon number 3 you have there the OH, and on this phosphate group you also have the OH. So when the two nucleotides lie adjacent or lie below each other, so this is your phosphate group and this is your carbon, then this is your nucleotide, and then the organic base. So if this phosphate group lie to each other, then there is no way why these OH groups, okay, these OH groups, there is no way why they should not condense with each other to lose a water molecule. So the result that is formed is a nucleotide, okay, the two nucleotides that have condensed together, okay, with a phosphate sugar backbone. So you have this phosphate that is now binding this nucleotide with this nucleotide. So with further condensation, if the same thing happens, then you form, the same thing happens, then you form a polynucleotide strand. Now this polynucleotide strand, it is the one, it has a phosphate sugar backbone with organic bases that will be oriented inwards at right angles, okay, at right angles. So we can have a look at that. So when the phosphate condenses with the OH on the carbon, then you form a phosphodiester bond, and that phosphodiester bond that is going to link these different nucleotides together. So you can have a look at this. So this is a nucleotide, the whole of this is a nucleotide, sorry, from here the whole of this, it's a nucleotide, even from here the whole of this, it's a nucleotide, and also the whole of this, it is also a nucleotide. And you can have a look how these nucleotides are joined together. They are joined on carbon number 3. The OH there condenses with the OH on the phosphate group of the other nucleotide, and the phosphate group joins on the nucleotide on carbon number 5. This one, this is carbon number 5. And so further condensation occurs, okay, further condensation occurs, and you end up forming a polynucleotide strand, okay, a polynucleotide strand. But because on the pentose sugar, if you consider this, the upper sugar, this one is going to be 5 carbon, this is the 5th carbon atom, and down, okay, this is the 3rd carbon atom, and the same thing will happen. It is the 3rd, it is the 3rd, it is the 3rd. So therefore, when we are giving direction to this polynucleotide strand that is formed, it is either going to be the 5, and then we put this one means prime, to 3 prime direction. Okay, so this one reads from the 5 to 3 prime. But if we want to consider the downer part, you see this one is carbon number 3, and I believe this one was also carbon number 3, but this is carbon number 5. So if you are to read going upwards, then this one becomes the 3 prime to 5 prime. And in DNA, for instance, these strands, they are anti-parallel, that each strand faces in its own direction. So basically, that's how a polynucleotide strand is going to be formed. Now, for the case of DNA, let's briefly talk about it. You saw that DNA is made up of 2 strands that are twisted together, that are wound together to form that double helix. You remember that? Yes, we talked. You saw it from the very first slide. But for RNAs, they just made up of a single strand. Okay, and these are organic bases. And actually, there are these organic bases that are strong enough to bind the 2 strands close together. Okay, now for the case of DNA, the 2 strands, they both do orient their organic bases inwards. They both do orient, if I'm to unwind, they both do orient their organic bases inwards. Where this one, the bases will be like this, and this one, the bases, okay, the base, okay, the base. Now these bases, like we said, if you remember in chemistry when we studied bonding, let me take you back, and to be specific, the hydrogen bond. We say that in a molecule where hydrogen is directly bonded to 1 nitrogen, 2 fluorine, and 3 oxygen, then these molecules do form hydrogen bonds within their molecules. They do form those intermolecular forces of attraction, the hydrogen bonds within their molecules. Now, we have seen that our organic bases, they have nitrogen that is directly bonded to hydrogen. You can have a glimpse. But also because oxygen here and carbon, they have totally different electronegativity values. Even here, different electronegativities. Then, it doesn't stop oxygen to attract the bonding electrons more to itself and gains a partially negative charge. That this partially negative charge can get attracted to the partially positive charge, hence forming hydrogen bonds within these organic bases that will hold the 2 strands stable and close together in DNA. Not so? Yes. And this accounts for the base pairing rule. Because it's not that each base will just pair with the other. No. You can actually see some bases are forming 2 Others are base are forming 3. Other bases are forming 3. Okay? So the base pairing is specific. That base guanine must pair up with base cytosine. A purine is pairing up with a pyrimidine. And base adenine, which is a purine, is pairing up with base thiamine, which is a pyrimidine. That base pairing rule is there, specific, untampered with. And by the way, that's what maintains the sequence. So the second type of bonding, other than the phosphodiester bond, is the hydrogen bonding, which occurs, which is formed between the two base pairs. Okay? And there are these hydrogen bonds that do maintain the structure intact and stable. Okay? Whereby in DNA, base adenine, as you can see, this is adenine, is going to pair up with base thiamine, and you form two bonds. A purine is pairing up with a pyrimidine. Adenine pairs up with thiamine. A pairs up with T. If you understand this, then trust me, you be kawa. Okay? And then base guanine, it will pair up with base cytosine. Base G is going to pair up with C. But now in RNA, it is kinda unique that base thiamine is replaced with base uracil in RNA. All ribonucleic acids, they lack base thiamine, and base thiamine is replaced by base uracil. So normally, base adenine, so the base guanine is going to pair up with base cytosine. Similarly, base cytosine is going to pair up with base guanine. So in RNA, like I've told you, sorry for that, you don't have base thiamine is replaced by base uracil in RNA. We are going to study all these structures and you shall appreciate. So base RNA don't, all RNA molecules don't have thiamine. They do not have thiamine. Okay? But the thiamine is replaced with uracil. And they are all pyrimidines, so no problem. So now, normally base G is going to pair up with base C, or base C is going to pair up with the G. But if you have A and you want to form thiamine, and you want to pair up, and you want to pair up in RNA, instead of T, then we shall pair up with U. But in case you have, for instance, T on the DNA, we are going to see all of this. I'm just trying to introduce you to a new concept. So if you have T on the DNA and you want to pair up with an organic base on the RNA, then we shall add A. Because A is found where? On RNA. But T is only on DNA, okay? But not RNA. And then base U on RNA, it will pair up with base A. And base A on RNA, it will pair up with base U on RNA. So if you understand this base pairing rule, we shall talk about it. We shall use it more frequently. if you understand this base pairing rule, then you'll be kawa, you'll be good to go. I'll give you some little work. So basically, adenine pairs with uracil and guanine pairs with cytosine. And adenine and thymine are linked by 2 hydrogen bonds. You can have a glimpse. Whereas guanine and cytosine, they are linked with 3 hydrogen bonds. And one base belongs to the purine family, while the other must belong to the adenine family. So basically, those are the bases. Let's talk about some few base pairs. You code for me this. You have this sequence of DNA. You have AG, you have C, you have T on DNA, you have A, you have T, you have C. So from the base pair, and you want to form another strand of DNA. So this is DNA, this is just some intro, and you want to form another strand of DNA. So from the base pairing rule, T pairs with A on DNA, and A pairs with T on DNA. C pairs with G with C on DNA, and C pairs with G. So here where you have A, on the other strand we shall put T. Here where you have G, on the other strand we shall put C. Here where you have C, on the other strand we shall put G. Here where you have T, on the other strand we shall put A. Then this one is T, then this one is A, then this one is G. So we are going to see, we shall talk about replication, okay? And we shall talk more about the base pairing rule. Not so? Yes. So this one is just to introduce you to this, so that you appreciate that there is no mistake as far as replication pairing is concerned.